Hello, everybody. Welcome to another discussion in dynamics. Today, we will continue our momentum of particles topic. And we will focus on oblique impact and constraint impact. And we will do two examples. Okay. So without further ado, let's dive straight in our discussion. Let me do a brief lecture review. Aha, I need an empty board for that, yes? So I think I will just, I will do it here. Oh, I don't need an empty board. I will just do it here. Okay, so I just want to review oblique impact with you. So last week we did direct impact, yes? Last week. It was direct impact. But today we will do oblique impact. So let us imagine a similar situation to the one last week. So we'll have a small particle and big particle. And this is situation pre-impact. And we'll also have something post-impact. Okay, so right now we will have, actually no, let's draw them closer to one another. I changed my mind, sorry. Let's draw them closer to one another. So this guy will have velocity, let's say, VA pre. Yep. And this guy will have velocity, let's say this one, VB pre. So our goal is to just find the situation post-impact. We don't know velocities post-impact. So how do we do it? We just project these two velocities on normal direction, so this direction, and tangential direction. Okay, so we will have this component and this component. So this will be VA pre tangential, and this will be VA pre normal. And we'll have analogical situation here. VB pre normal and tangential. Okay, so in order to figure out what happens post-impact, we actually don't have to do much. First of all, we have two informations for free, because we know that this component will be these components will be unchanged. Okay, so we know that. So I can just write that these guys post are equal to their counterparts pre-impact. Yep. So this guy is equal to this one, and this guy is equal to this one. Okay, everything clear so far? Yeah, okay. And what do we do? And now question to you, what do we do to find components along this line? We repeat exactly what we did on Friday. Yes, we repeat exactly what we did last time. Okay, so I think we can stop here. Yes, do I have to finish the drawing? No, just I can do, in order to find what happens along that line, repeat our solution from Friday. Use what you learned last time. Okay, any questions? Okay, if I don't see any questions, so let's do example number 1. Please familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? Okay, so we have two particles. And we have a situation pre-impact here, and situation post-impact it will be on the board. Yeah, don't worry. Yeah, so we know that one of them is a liar. Yes, one of these drivers is a liar. Yeah, because he or she claims that they were traveling according to the rules. Okay, so let's figure out who is a liar. Yeah, this is our task for right now. What I would like to do, I would like to draw a situation pre-impact and post-impact. Okay, so we will model our cars as particles. Okay, do we know what Murphy's law is? Did you notice that something is wrong with my tablet today? So my tablet was working fine even yesterday in the evening. I think that it's too smooth. I must replace the cover. Yeah, I just need more friction here. That's why it's so slippery. I cannot write in a normal way. Okay, I will play it by ear. Okay, let's do it. Sorry, guys. Yeah, you notice that something is wrong, yeah? It's annoying. Sorry. Yeah. So I'm just gonna model this guy like that particle. Okay, and this guy is traveling this way. With MA VA, and that angle is 30 degrees. And we also have another particle traveling this way. NB VB. Okay, and post-impact, they will just be glued together, if I can say so. Okay, and then they will have such velocity. Let's say MA plus, let's say V final, okay? and this is 10 degrees. Okay, so in this problem, what's different in this problem than in most of the problems, than in 2 problems we did earlier? In here, we cannot specify where is line of impact and where is plane of impact. Yeah. So, but we will, then that problem can be solved without this knowledge, because we know that momentum is preserved in unconstrained impact. Yes, momentum preserved during impact, but unconstrained. Unconstrained. And this is unconstrained impact clearly because we have no constraints in the system. We just have 2 particles. So we can write what happens in the x direction and what happens in the y direction. Okay, and these are our positive directions. So in the x direction, I believe that at the beginning we have MA VA times cosine 30. And at the end, we have MA plus MB V final cosine 10. Okay, in the y direction, we have MA VA sine 30 minus MB VB. And at the end, we will have MA plus MB, exactly the same as in equation number 1, just there will be sine instead of cosine. Sine 10. Great. Okay. So now, how many equations do we have? 2. 2 equations. And how many unknowns? This is not known. This is not known. And this is not known. 3. 3 unknowns. However, we will not find the third one, because that problem can be solved even without the third equation, because they do not ask us to find each of these 3 values. They just ask us to find a ratio. They ask us to find this. VA divided by VB. Okay, this is what they ask us for. So let's just dive straight into solving that problem, and I bet we can solve it. And what I want to do, I just want to divide equation number y divided by equation number x. Okay, so I'm just going to copy. I'm just going to copy this. This is equation number y. I'm just going to divide this left-hand side by the left-hand side. And I'm going to divide the right-hand side by the right-hand side. I can even do it in a smarter way, because I can divide this into 2 fractions, right? I can do something like that. And I can copy that, the numerator as well. Okay. Wait a second. I think I can make things smaller. Okay, and you can already see, guys, that some things will cancel out, right? So first of all, what can we cancel out? Aha, we can cancel out this thing and this thing. and this thing, and this thing. Wow. And we end up with tan 30 minus MB MA VB VA 1 over cosine 30 is equal to 10 degrees. Okay, so this is the only unknown, as you can see, guys. This is the only unknown. I have no doubt that you can solve that equation for this ratio. We will have VB divided by VA is equal to approximately 0.4465. Okay, problem is almost done. Who is a liar? Which velocity is faster than another one? VA is faster, yes. So VA must be faster than VB, and VA is a dirty liar, yes? We can write driver A is a liar, maybe dirty even. Okay, this is the end of part A. Now part B. They ask us to find what was velocity of VA if VB was driving according to the rules, right? So based on this equation, we can just write that VA is equal to VB divided by 0.4465, and this thing is 30. This thing is 30. So VA is approximately 67.185 miles per hour. Okay, this is the end of the problem. Okay, I'm gonna erase that dirty. I thought it would be more funny actually. It's not. It was not that funny actually. Sorry. I don't have chance to test my jokes before coming here. You are the first discussion I am teaching. Okay, so you are the experimental bunnies on my amazing jokes. Okay, any questions to what happened? About what happened? Yeah. I think recently one American guy, he like beaten the world record in shot put, like last week or 2 weeks ago, I believe. Okay, doesn't matter. Sorry, doesn't matter. Sorry. I apparently live in a different world. Yes. Okay. Example number 2. As usual, please read and understand the problem statement before we start our solution. Okay. That problem statement is very short, right? But the solution will be long. Okay, so this is very specific example of impact. This is called constraint impact. Why? Because clearly you have a constraint in the system. Yeah, that rod is our constraint. Okay, so we have our this ball is dropped on the other ball. They both have mass m. They both have the same radius. And we know what happens pre-impact. Yes, we know what happened pre-impact, and we know that heat is elastic, perfectly elastic. What they ask us for? They ask us to find what happens after the impact. Okay, so I would like to start our solution with this, with just figuring out a little bit one missing information. So just let's draw these two spheres during the impact. Okay, let's connect their centers, and let's figure out what is this angle, this green angle. Let's say theta. But we know some more, yes? We know that this distance is 2r, and this distance is r. So I believe that based on that black triangle, we can write that sine theta is equal to r divided by 2r, which is 1/2. And that clearly tells us that theta is 30 degrees. Great. Part 0 is behind us. Now, I solved that problem yesterday, and I needed like 2 or 3 attempts just to solve that problem, okay? So let's start with momentum diagram for the entire system, okay? Let's look at the entire system and let's see what we can get from it, okay? So now momentum diagram. For the entire But don't understand me wrong. I like that problem. I like that problem because it is actually shows us how to interpret physical phenomena in our world. Okay. So so what are we gonna do? I'm gonna draw 2 balls 3 times. Yes. So I'm gonna do ball in here and ball in here. But I'm also a liar. I'm not gonna draw them. I'm gonna copy paste them. Of course, you must draw it. Here, here, and here. Okay. So what happens before the impact? This guy has velocity, mv0. The other guy has no velocity. Yeah, they told us that the other guy is at rest. What happens? So let's do forces right now. So mg acts this way, mg acts this way, and there's also one more force in the system, this one. Tension in the cable, right? Okay, just on a side note, you know what I said, that mg's can be neglected. Okay, so I draw them, but we can actually neglect them. Negligible. But anyway, you guys see that every single force points in the vertical direction, yes? No forces acting in the horizontal direction. Okay. So momentum will be preserved along which direction? This one, exactly. Okay, and what happens after the impact? Can you guys tell me what is velocity of this particle, of the one on the bottom? Can you tell me which direction that particle will have? Yes, Hamilton, and why? Perfect, exactly. So the trajectory of that particle is a circle, yes, because of that constraint. Perfect. So yeah, I think that it will be pointing this way. Yeah, so that would be, how do I call it? I call it M VB post. All right, and can you tell me which direction will be velocity of this particle? Can you guess it? Yeah, but yeah, what's the angle? We don't know. We don't know. Yeah, exactly. So that velocity will have definitely two components. Yes, and we must figure them out. So I was figuring out yesterday what is the best coordinate system to put these two velocities in, and I figured out that the best coordinate system is this one. Of course, my tablet is listening to me today. Yeah, this one. Normal direction and tangential direction. Okay, so let's say that this guy will have this velocity. MVA post T. And which direction do you want to assume, guys? Do you want to assume this direction, this one, or this one? Which one do you want? It doesn't matter. Yeah, we will solve that problem anyway. Okay, so I will choose. Let's say this one. So this will be MVA post normal. Yeah. Okay. So you guys, okay, and let's not forget about our integral. Plus integral from 0 to, or like T0 to T final, or actually 0 to T final, dt is equal to that. Okay. So you guys told me that there are no forces in the x direction. That means that momentum preserved in the x direction. Okay, so what can we write? Oh, we can just write that. So we have 0 plus 0, and this is equal to, let's define our direction, positive direction, this one. So that will be minus MVB post. And we have to do some projections here, yeah? So this green guy will be this component, and this red guy will be this component, okay? So we will have plus MVA post T, sine or cosine here? Cosine 30 degrees, and I changed my mind. It won't be red guy, it will be blue guy. And here we'll have plus MVA post normal sine 30 degrees. Okay, so this is our first equation. So first equation, how many unknowns do we have? I'm afraid that we do have 3 unknowns. 1, 2, and 3. So we need 2 more equations. Okay? So now, everything clear so far? What we did? Yeah, we just look at the entire system and we found 1 equation, yes? And by the way, okay, so what's the other idea, guys? Yeah. Do you want to go for equation along this direction? Do you think it's a good idea to go for the equation along this direction? I mean the vertical one. I think it's not a good idea. And can any of you tell me why it's not a good idea? John? Okay, so the answer is that I am looking for more equations, yes? I'm looking for more equations right now. And I do not want to introduce more unknowns. Please look at that direction. Do you know T? No. Do you know TF? No. So if we go for equation on that direction, we'll introduce one more equation, but two more unknowns, yes? Not a good idea. However, we have a freedom to not only look at the momentum for the entire system, we can look at the momentum change of each body separately. Let's look at the momentum of only the upper body, okay? So now we will just leave that equation here, and now let's look at the momentum of the other body, of the upper body, okay? Upper sphere or ball. Okay, so this time I will just draw one ball 3 times. And of course I'm lying again. I'm not, I copy paste them here and here. Okay, so what happens before the impact? Before the impact we have this velocity only. Yes, we have mv0, and after, let's have the same situation, okay? After we will just have this situation. Copy enter. Uh-oh. Afterwards, we'll just have this situation. Okay, so now let's see what forces act on our system. Just let's draw that mg. It's negligible anyway. And there is one more force acting on our particle during the impact. Anybody want to help me? Yes, Jason? Yeah, let's do it N. Okay. You guys seem like low energy. Yeah, today. Why? Something happened? Really? Yeah, do you know how many hours I slept today? Yeah, it's okay. Yeah. And no, I don't drink coffee, by the way. Yeah. I cut it off 3 months ago. Amazing time. Yeah, the best time of my life. Yeah, I recommend it, guys. No, don't drink coffee. But I still like you, man. Yeah. Okay, so now the only force acting on our system is in the normal direction, yes? So momentum of that ball will be preserved in the tangential direction, yeah? Yeah. So now, no forces in the t direction. So momentum preserved in that direction, yes? In that direction. Okay, so we must do some projections here, yes? So we need this component. And this will be mv0 sine theta, sine 30 degrees. So we just know right now that let's write momentum for the t direction, with this direction being positive, and here we will have mv0 1/2, yeah, because sine 30 degrees is 1/2, and this is equal to mva post t. Great, because we just found that one unknown. So we just found that va post t is equal to 1/2 v0. Great. Hooray. Okay, so if I scroll up the board, we just found this one. Yep, but still we have two unknowns. Yes, we still have two unknowns. Yes, so we will just, there is a way to solve that problem. Yes, Jason, you have a question? Thank you for remembering me. Negligible. It's negligible during the impact. Thanks. Okay, I think so far so good. So, any other idea how to find third equation? I think we didn't use all the information they gave us. Yeah, let's use coefficient of restitution. So now we will have coefficient of restitution. So again, I will just draw these two balls. And again, I'm lying. I'm going to copy. I'm just going to draw them here and copy them there. So this is our line of impact. This is our line of impact. And before we have such situation, yes, that before we have mv0 cosine 30 degrees, yes. What I did, I just knew that we have this velocity before the impact, but we care only about that component, yes. The other component we have for free during the impact, and afterwards, let's assume that we have these two velocities. Let's assume that we have these two velocities. So this will be VA post normal, and this will be VB post times sine 30 degrees. What I did, I just took that component of this velocity. Yes, so that was our VB post. Yeah. And by the way, you can erase that M from here. That M is not needed. Let's erase it. Okay, so what is our coefficient of restitution equation? It was E delta V post divided by delta V pre. Okay, so we know that this will be VB post sine 30 degrees minus VA post N, and 3 will be V0 cosine 30 degrees minus 0. And by the way, this is 1. Okay, so we found our third equation, because this will be V0 cosine 30 degrees, and this is equal to VB post sine 30 degrees minus VA post N. Okay, This is our third equation. Okay, guys, so what's the next step? We have two equations and two unknowns. Yes? Unknowns are red. That's solvable. Yeah. Plug in values wherever you want and solve for VB post and VA post N. Sorry, N. Okay. And you will find that this guy is approximately 0.693 V0, and the other one is 0.520 V0. Okay, so if I may steal 30 seconds from your time, I just would like to draw the situation post-impact. So this is how our situation will look like. This will be 0.693 V0, and this guy will have such components, this direction, this direction. This will be 0.5 V0, and this one will be 0.520 V0. Okay? So actually our VA post will be 0.5. Doesn't matter. Let's maybe just find the magnitude. Okay, so the magnitude will be 0.721 V0. This vector is 0.721 V0. Okay, questions? It was probably one of the most physical problems we solved this semester, yeah? Because it clearly like enforces you to look, what happens along that direction, yes? And to neglect the other direction, yes? Then look at that direction, yes? I don't know, chew on it, and maybe you can have some questions on Friday, okay? See you, and hope to see you on Friday.